to the February ARA general meeting. And I'm going to move around so James can't keep me on camera. I'm going to be difficult tonight because my dinner just arrived, so I'm not happy. Let's see. Just a couple updates on things. I think all of our sites are working. Am I correct, Mr. Campbell? There's nothing that's challenged right now?
You're not quite right on that. We have one challenge, and that is the link between Ord and Pinnell went down last night or yesterday sometime. So Pinnell is off of RimLink at this time. Other than that, everything seems to be working right. I've seen no other faults or anything.
Okay, thanks for that. And with all the weather, it could be ice. We're lucky that all of our sites are still up. I know at least one tower that went down as a result of the storm yesterday. It wasn't an ARA tower. So also just on the public service side, we've got some events out there that still need people to sign up. If you're interested in doing that, go to the MCECG website. And also those of you who are looking for an Oxcom class, there's one going to be offered in Maricopa on April 1st and 2nd. And if you need information how to sign up for that, you can just email me and I'll get you that information. So let's go around and do introductions of who's here. Since how many we have online? We have a few online too tonight, right?
Yeah.
James doesn't have the big screen up, so I'm in the dark.
Oh, here.
So we're going to go around and everybody name and call sign.
Michael, WB2SEF.
James, N7ELL.
Clark, KI7TU.
I'm
John.
No, I'm John K7LK on my 65 known 65 known partner.
Yeah.
Donna.
Soulmates of 65 years.
And I think we gave you the call sign of N0NE the last time. Oh, and by the way, I guess I forgot to introduce myself. I'm Dennis KE70JF. And let's see, who else do we have on? Mr. Campbell, you want to introduce yourself?
Okay, I am Dennis Campbell, AE7WU.
Thanks, Leonard.
Leonard Pennock, 87AS.
Patrick. Tom.
I'm in L7FQ.
And Phil?
Oh, this is Phil, AE70H.
And we've got one that we can't see your name on the screen. You got a blue shirt on.
Jim.
You. Oh, there you go.
Jim.
Sorry, Jim.
NK2J.
He had it moved. Yeah, we could only see a part of the screen. All right. So I guess at this point, we'll turn it over to James for his presentation tonight.
Okay. Great. Well, I've been having trouble trying to find a few folks to come and talk to us. And so not finding somebody, I decided to put together a slide deck. And tonight, let's get this out of the way. Okay, everybody can see that, I hope. Full screen.
Yep. Yeah, it's working good here.
Okay, good. All right. So I thought I would talk about some basic antennas and a little bit of modeling software. I found out not too long ago, I don't know how long ago it actually happened, but recently anyway, Roy Llewellyn, W7EL, I believe this is called, up in Beaverton, Oregon. For many, many years, he has been putting together EasyNEC, EasyNEC, and that stands for easy, meaning it's easy to use, numerical electromagnetics code. And you can use it to describe antennas and model them and predict how they're going to perform. And you do it by drawing the antenna using what they call segments or wires. And you can build just about any kind of antenna you want out of these segments. And it does a pretty good job of pretty accurate for what it is. Well, he's decided that he's going to retire from keeping this software up, maintaining it. And so what he's done is he made the last changes and the last bug fixes, and then he released it to the public. So it's freely available now. You can download it, install it, run it. It's EasyNet 2.0 plus, version number 7, and freely available. And so at the end, I'll go over some of the examples that you can look at and get an idea of how to set things up so that you can build your own antennas inside of it, and then actually go out and cut some wire and see what you come up with. So I thought I'd start off with the easiest antenna that you could possibly make, and that's a dipole. Very simple, just a piece of wire that you cut to a particular length. And, the people say, well, okay, for the dipole, I got to take 468 and divide it by the frequency in megahertz, and that's my half-wave dipole. And that's for here on Earth, because we have dirt and other things that surround the antenna. And so it changes its effective length a little bit. If it were out in space, in what we call free space, so there's nothing around it, so someplace in outer space, it'd be closer to 492 that you divide the frequency into. Well, why do we divide say 468 by the frequency in megahertz? Where in the world did they come up with 468? Well, if we take a quick look at the free space value, it's actually, when you compute it, it tells you how many feet, how long does the wire have to be in feet. So if you take 492 feet, you do some conversions to get it into the metric system. And since it's a half-wave dipole, we have to multiply by 2 half waves. You get 300 meters. And so, well, what's so special about 300? Why 300? Well, wavelength is related to frequency by the speed of light, which is how fast radio waves travel. And so both radio waves and light travel at that speed, 300 million meters per second. That's where 300 comes from. And in fact, if you look at the frequency tables, they'll be listed in ranges of meters. So you look and you'll see, well, there's 1,000 meters to 100 meters, 100 meters to 10 meters, 10 meters to 1 meter. Well, that converts to frequencies, and you end up with 3 megahertz to 30 megahertz, 30 megahertz to 300 megahertz, 300 megahertz to 3 gigahertz. And so that's why the frequency tables are listed that way, because initially, when they started building radios and so forth, they listed everything in meters. They didn't say how many hertz you had. In fact, frequency wasn't named hertz after Heinrich Hertz until much, much later. You might hear some people say frequency is called cycles per second or kilocycles per second, because it was a cycle of a sinusoid, a sine wave. And so they didn't have a name for it yet. And it was only later that, I forget when, maybe somebody can look that up, somewhere in the 60s or 70s, perhaps. Was it in the 60s? Clark, our resident historian, is telling us it was in the 60s. but it was recent, so to speak. It's within 60 years ago. But in any event, that's where all that comes from. And so A dipole, since it's a very, like I said, a very simple antenna, you might think that perhaps it's resonant at 50 ohms. Well, it's not quite at 50 ohms, but it's close. So it's not too far off. It actually turns out it's just a hair over 73 ohms of reactance and resistance or impedance. And it's not fixed. That's on average. So if your antenna happens to be a little different height off the ground, it will change its impedance. And so if you're very close, say a quarter wavelength off the ground or close to a quarter wavelength, you'll be close to 73 ohms or 70 ohms, which is, if my pointer, get it over here, which is somewhere right about here. Hopefully you can see the pointer. If it's a half wave, well, that's a little closer to here somewhere. That's about 73 ohms. If you start moving in multiples up, you can see that it's finally, you're getting closer and closer and closer to, as you get further and further from the ground, you're getting closer to free space. And so if you got all the way into outer space, it should level out at about 73 ohms. But height does make a difference. And so, well, this little tiny resistance difference between what the dipole is resonant at versus what the coax is resonant at, 50 ohms typically, that gives you a little bit of voltage standing wave ratio. And so you end up with something close to 1.5 as a standing wave ratio. Well, what the heck does that mean? You know, it means that you have some of your signal that's bouncing back and forth between the antenna and your radio. And if it's large enough, the voltage that's induced, that's voltage standing wave ratio, let's say it's, for some reason, it's 10-to-1. It's enormous. So the power is going out to the antenna, reflecting back, and creates a very high voltage on the input of your radio. Well, most solid state radios can't handle that really high voltage that's being produced by that standing wave. And so they will automatically today, they didn't used to, people would blow front ends out of their transmitters all the time, blow out the finals, because they put too high a VSWR, too much of a mismatch, and it would be produce too high a voltage on the output transistors and blow them up. Well, today radios are a little smarter. They put in a circuit in there that detects that there's a high SWR and cuts the power way back so that it maintains it below a voltage that the output transistors can handle. And so you'll see the radio fold back really quickly, perhaps to 1 watt to protect itself. And so you can see this. I snagged a picture of an old Heathkit SWR meter, and so that you could kind of get a sense of, based on SWR, it also happens to list the percent of power that's reflecting back and forth each time in the coax. And so if your coax is lossy, you could be putting a lot of energy into heating your coax. And so you may not create enough energy to melt it, but you're effectively just heating up the atmosphere, and the power is not going out the antenna and being radiated to make contact with somebody. And so it's wasted energy creating heat. So what if we just wanted to make a simple antenna, a dipole? Well, what if we just make one that works on 2 bands simultaneously? You could cut a dipole for 40 meters. And so that's roughly 66 feet in length. And it will also work on 15 meters because that's 15 meters is also the 3rd harmonic of 40 meters. So on 40 meters, you'll have a half wave dipole of 66 feet, roughly. But on 15 meters, you'll have 3 half waves. And so on the left up there, we can see that it has the traditional dipole radiation pattern. The antenna is horizontal in that picture, and the lobes come off from the broad side of the antenna on both directions. And you make contact in those directions. You may get some minor lobes coming off the end of the antenna, depending on how high off the ground it is. The closer you get to the ground, you get what's called near vertical incidence radiation. And so the signal, you'll have lots of side lobes, and those 2 lobes that are shown there will start to merge into one big circle. And the signal will go almost straight up and come almost straight back down. And so you get a very tight radius that you can make communications within. So you can go up and over the top of mountains with it, or that sort of thing. On 15 meters, though, you have something that looks much more squirrely. You end up with this 6-lobe pattern, and the main lobes are roughly 42 degrees off from the antenna. And so you could actually hear and talk with people readily well in those directions, 4 different directions, and somewhat broadside. Not quite as good a signal, but you've got this multi-pathed, multi-lobed antenna, but you've gotten 2 bands out of 1 piece of wire. Well, you could make the antenna longer. You could make it 2 wavelengths long, and the picture didn't turn out so great, but if you do 2 wavelengths, it'll be resonant and it'll work on 40 meters, and you end up with even more lobes. In that case, you have 8 different lobes coming off. Well, what about if you make it even longer, 5 wavelengths? Well, now you get a whole bunch of lobes in the middle and two prominent lobes on each end. Well, what about 8? It gets even better. You get these 2 long prominent lobes coming out of both sides and a whole bunch of short ones right in the middle coming off the broad side. And that's the beginnings of the next antenna. How could we take advantage? If you have a lot of space, let's say you have 10 acres and you wanted to put up antennas, wire antennas are pretty tough to beat if you have the space. And so you can start thinking about really long antennas. Well, how can we take advantage of this 8 wavelength long antenna? Well, you can make what's called a V antenna. So you take 2 really long antennas and you separate them by an angle. And now you can start adding the lobes together. So lobe 1 and lobe 3, lobe 2 and lobe 3 will add together, and you get the pattern to the right. So you have this really long lobe and a bunch of little tiny short ones behind it. So you can get a lot of gain out of just 2 long pieces of wire at the appropriate angle based on the frequency that you're going to operate. And so if you make them even longer, or if you terminate them, if you put a resistor at the end of the wire and just don't leave it open-ended, well, then you get 4 lobes, and you can add all 4 of those together, and now you get a bidirectional pattern. So you can hear equally well in both directions and very little to the broadside, or what would be the broadside of the antenna. Well, what if we took it just one step further? You must have a lot of land because the next step is let's build a rhombic. I'm sure some folks have heard of a rhombic antenna. Now there are many, many wavelengths on a side. Usually there are at least 3 wavelengths on each side. Some people have gone to 5 or 6, but 3 seems to work. 4 seems to work. They're big. I mean, if you put 4 wavelengths, 40 meters, 4 times 40, 160 meters just for one of those legs. And then you're going to have two of them, and they're offset at a little bit of an angle, but two of them end to end. So you're probably going to have a length of about maybe, if it were straight, it'd be 320, but you're going to have an angle in there more like a rhombus, and so a squashed square. So maybe it's 250 meters or 200 meters long by the time you're done. That's a pretty long antenna. Now there's two ways to do it. One is horizontally. So it looks like a gigantic loop, you might say. Maybe you have telephone poles and you put a telephone pole at each apex. And at the far end, you put a resistor there, a pretty big resistor, because depends on how much power you want to run. So, but you need a non-inductive resistor out there. So you don't want a coil of wire acting as your resistor, because that coil of wire, it works well as a resistor for DC, but it doesn't work worth a darn on any frequency that we want to operate. So you need some sort of non-inductive resistor out there. And they make those. You can get metal film resistors or heavy-duty carbon resistors that minimize that inductance. And you can get them in pretty high wattages. Depending on whether you put a resistor out there, which end you put the resistor on, you can drive the direction to the right or to the left. Now, if you didn't want to put up two sets of wires and make a gigantic loop, you could do it vertically. And so that's the lower right-hand picture. And you still have about the same length. So, you still have for 40 meters, 4 wavelengths on a segment, you still have 160 meters of wire stretched out. And it would be fairly tall. So if you had a tower strategically placed, you could perhaps make a vertical, I would call it a half vertical rhombus or rhombic, and get directionality that way. I'm not sure how well that would work in Arizona because our ground conductivity is not that great. It's okay when it's wet. When it rains, it's just fine. It's when it dries out that it sucks. And so you might not get that image, which is shown with the dotted line. It'll be rather poor for having that mirror image in the earth. And so it won't work nearly as well as it would, say, in Virginia or someplace where it's the ground conductivity is much higher. But it works. So as I was saying, EasyNet, Roy Llewellyn, he decided that he's going to retire. He's, I believe this year he turned 77. So he's going to take a break, and he's written tons of articles. If you just go to the ARRL website and search within QST for his call sign, you'll see a plethora of articles that he's written about modeling antennas and using EasyNet and all different types of designs over the years, over the last probably 30 plus years, maybe it's closer to 40, for a long time. The NEC program, the new numerical electromagnetics code, was actually written, I believe, for the Navy a long time ago, back in the maybe late 70s, perhaps, when they started. And so it's gone through several revisions. It used to be for a long time, you had to get a special license to get version 2. They eventually came up with version 3, and then 4 became really popular. I don't know if they still have those restrictions. Last time I got NEC 4 from Lawrence Livermore, it was still under restriction. And so for a US citizen, it's not much of a restriction. You sign some paperwork that you're not going to sell it to the Chinese or give it to them, and you're off and running. I think there's also an NEC 5 that came out, although I haven't looked into it to see how you get it, if it's from the same location or who has it or whatnot. But in any event, Roy has generously, in my opinion, given out this software for free, but there's not going to be any support for it. And so you can go to easyneck.com, download it, install it, and start building your own models and trying to cut wire and try to make your own antennas. And so I've got a few examples here. Let's go here. And oh, hide. All right. Well, that's a little big on that screen. Okay. So this is just an example of a Foursquare. And so if we want to view the antenna just to look at it, oh, it pops up on the other screen. Let's get that over here so you guys can see it. So it just shows up, it shows you the coordinate system, the XYZ coordinate, so you can figure out which orientation you're going to build it in. The segments are all these little green dots between the wires. It's a little tight here. Let's see if I can zoom in a little bit. Display. Yeah. So the wire is actually the segments in between the little connectors here, and you can break up the wire into pieces so that you get a connection between, and that's what it's actually calculating, is at each of these points. And so you want lots of separation or lots of breaks in between, so you have lots of data points for it to compute. It's basically doing a finite element analysis. And then it's showing in this purple or pink colored lines, it's showing what is the current that is flowing in the antenna. And then down at the bottom is the connection. So this is a source connection that's being driven. And so this is modeling a Foursquare antenna. So you have 4 verticals together, and depending on how you phase them and drive them, you can change the direction of the signal. And so the direction of where you're listening from and also transmitting to. And so that's what this shows, is if you were to look down on top of the antenna, you could see which direction the antenna is listening or pointing towards. And so your antenna is here at the center, and this is what's called the far field presentation. And so you're assuming that your 4 antennas are so small inside here that you can't really see the antennas, but this is the pattern at, say, hundreds of miles away, what it would look like. And so you end up with this very sharp null in the back, what we call the back. So you don't hear much to the southwest position, but you should hear quite well out to the northeast position. And by the same token, by reciprocity, you get the same transmit gain as you get receive gain. And so they will hear you better in that direction also. And so you can play around with this and do all the tinkering that you like. And when you're satisfied with what you've got for an antenna, then you can go back and look and see what measurements you actually ended up with and how much spacing you had between elements, and actually then go out and try and build it. Now, it'll also compute for you the SWR. So we don't want any reflections coming back, and It's a lot of people say that SWR doesn't really matter. Well, it doesn't matter until it does. And that's usually if you have a solid state radio that gets upset. The old tube radios didn't care because the old tube radios had a very high impedance, much higher than 50 ohms. And so you actually had a pi network inside them that would tune the 6,000 ohms you had of impedance at the tube down to 50 ohms. And rather than the other way around, which most transistor radios, you're tuning up in the impedance spectrum. So you're going from say 2 or 3 ohms up to 50. And so a little different there. But anyway, you can compute what the SWR is. And you can tell it, let's just force it to do it again. So if we tell it, let's close it. Seeing as how I already did it, or did I? Oh, it dumped it over here. Sorry. Have to move it over here so you folks can see it. So since it should be somewhere in the 40 meter band, around 7.2, 7.3 megahertz, I just decided to run it from 6 megahertz to 8 megahertz in 50 kilohertz steps and tell it to go and compute. So it's racing over here. If I can grab it in time. Oh, it finished. Okay, good. So it computed, and so you can drag the ball here along the line, and it'll tell you then what the SWR is, what the impedance is, at what angle, or how much reactance. And so you can see, or it will calculate and tell you what you should be measuring. So if you happen to have one of these cute little antenna analyzers, MFJ makes one that has analog dials on it, so you can read the SWR and change the frequency and see where it lines up. If you have something a little more fancy, like a rig expert, it will actually give you these numbers if you wish. It'll tell you what the resistance piece is and what the reactance piece is. It'll give it to you in impedance and an angle, a phase angle. It'll give it to you in reflection coefficients, return loss, just about whatever you ask for, it'll give it to you in. But it'll scan the entire frequency for you and show you a nice display of what the SWR looks like. And so it's very quick to scan your antenna with, say, a rig expert across all the frequencies that you're interested in, because maybe your antenna, you're not quite sure what frequency it's actually going to be resonant at. And so, maybe you've designed the antenna to be resonant on 40 megahertz, or on 40 meters, 7 megahertz, but you may find, because of the surroundings, it may be resonant on some other frequencies that you may like to operate on. And because of those other obstacles, maybe it's your house is the obstacle that's next to you, next to the antenna. You may get lucky, and it may also operate on 20 meters, maybe a very narrow segment, but you may find something strange like that. And if you spent enough time, including your house in the model, you might actually be able to predict it and see it before you actually build it. But it's at least something that you're able to play with now and to learn about, and you don't even have to go outside and cut wire if you don't want to. You can stay inside and play on the computer and design antennas until your heart's content. But and now it's free, so anybody can do it. It's don't feel like you're left out. You can get this for free and try it out yourself. Does anybody have any questions? Oh, Clark. Oh, let me give Clark a microphone here.
Will it deal with non-driven elements like as in a Yagi?
That's a good question. It will, and oops. And you can So it'll handle Yagis. In fact, let's take a peek. I think he's got a Yagi in here somewhere. Let's don't save that. We can close this. Okay, let's see. I think he's got a log periodic in here. Let's look at this one maybe. Okay, where did it go? There it is. Okay, so here's a log periodic, and they're driving it from one end because all the elements are tied together. Now you were asking specifically about not having any driven elements, because in a log periodic, they're all driven. Let's see if he has another one in here. Let's see. Oh, here's one. Let's look at this. Yeah, let's view it. Okay, so this is a 5-element 20-meter beam. And so he has one driven element here near the back, one reflector, and 3 directors in front. And so you can include obstacles. So this is just modeling the antenna. But let's say your house is right next door and it's covered in chicken wire and stucco and makes a pretty good Faraday cage for our frequencies. The holes are pretty small compared to the wavelength that tries to pass through them. You could include out here somewhere your house. And so you could see what that does to the pattern and do some predictions. And so I wouldn't recommend putting a 20-meter beam with 5 elements at 10 or 15 feet off the ground. It would be better if it was 70 or 80 feet off the ground. And that way your house kind of is taken out of the picture. But you could do it. You could see what would happen. Maybe it's not your house. Maybe 300 feet down the road, somebody has a gigantic shed or some type of Quonset hut or an air hangar for an airplane, and you want to see what that would do to your signal. You could include that or try to include it in the model and see what happens. Are there other questions?
Yeah, James, I have a question.
Yeah.
Does the drawing environment lend itself to drawing a patch antenna easily?
Okay, so the drawing environment is not the greatest. The user interface is, I'll call it very old fashioned, and you're building the antenna out of wire segments. So it's not very friendly. Although I will say, once you do get the hang of it, you can quickly start putting things together. I haven't tried simulating a patch antenna, say for UHF and above, like 900 megahertz or higher. Maybe he has an example in here. Take a quick peek and see. He's got some 40-meter beams, some 4 squares, a quad, the 20-meter 5-element, some dipoles, a V. What else you got here? Log periodic. Yeah, I don't see a patch antenna as an example. That'd be interesting, something to see. See if you could actually do it. Although I haven't tried it. Does anyone else have a question? No more questions? Okay, well, if you do happen to have a question at some point, feel free to email me. I'm listed in QRZ. You can send it to my personal email listed there, or you can send it to n7ell@w7ara.net, and I should get it hopefully. The best part I liked is that I found out that Roy's given away his software. So, but so now I can actually go play, because I seem to remember he used to charge like $100 and some per copy. So it wasn't cheap. I mean, it's cheap compared to commercial software, but it wasn't inexpensive as far as for hams. You could certainly spend it, but in any event, the stuff I use at work is much easier to use, but HFSS from ANSYS and the modeling software to create the antennas is much simpler to use. That's the biggest improvement, really. This, like I said, uses wire segments, and so you have to connect and build all the segments in order to model it.
Yeah, the last time I used HFSS was over 20 years ago, and the license was $8,000 a year at that time.
Yeah, it's quite a bit more than that now. Yeah, and they've really updated. They bought this company called Space Claim that because their interface for creating three-dimensional models was terrible also, and so they bought this little company called Space Claim that really makes it simple to draw three-dimensional objects of just about anything you can think of, and bolted that onto the front end. And so you can create your models, whatever it is, from many different sources, not just drawing it. You can take pictures, and then it will create or try to create a 3D model based from a picture. So if you had an idea of what you wanted, you could cut some time that way. But yeah, but this works, and it's free. That's the best part. Well, thank you everyone for coming this evening, and thanks for the questions. And if you have more questions later, feel free to contact me. My email's out there, and I hope you try it and go cut some wire, make some antennas.
Thanks, James.